What's up, everyone? It is calc time, your favorite time of the day with Miss Wesley, and I know I'm glad you're here. Today we start a new unit, kind of some exciting stuff here on differentiation applications. So sure, we've spent a lot of time so far in calculus finding derivatives, finding rates of change, applying them in a few different contexts. And this unit that we're starting now is going to be all about how differentiation helps us sketch curves, give those curves maybe some real life meaning as well, and optimize functions, meaning we're taking things, you guessed it, to the extreme. We're finding maxes and mins on different types of functions. So before we get down to business, I was going to start with a joke. So to start things off, I saw a guy who was walking down the street and he spilled all of his Scrabble tiles on the street. So I said to him, "Hey, man, what's the word on the street?" At the top here, you might see a few vocab words that you recognize already from previous math courses and from the beginning of this year. Speaking of the behavior of functions, we're gonna be talking about where functions rise and fall. We're gonna be talking about a lot of maximum and minimum values, and you see a definition here of global or absolute maxes and mins. This point up here, this y value, is the highest y value ever attained by this function. It's the absolute max. And this guy down here, this point down here, whatever this y is the lowest y value this function attains. Now there's some importance in also talking about the local peaks and valleys. They'll call these things, maybe this is just a local or a relative max and a local or relative min. Nobody's trying to claim that that's the highest this graph ever gets to, but in this little neighborhood on a closed interval, that is a peak of the graph, and that's going to be important. Now we've got a few more definitions going down the page. And we have a theorem that actually we mentioned a while back when we were talking about limits. And it's called the extreme value theorem. And it says if you have a function that is continuous, has no breaks in it, on a closed interval, right? We remember that means an interval that contains its endpoints, it's inclusive of the two endpoints, then automatically EVT, the extreme value theorem, says that this function has to have a min and a max on that closed interval, an absolute min and max. Here's a function, here's just a little line segment that has a low point and a high point. There's no turning points in there, it's strictly increasing. And here's a function that's got a couple turning points. And on this closed interval from A to B, it attains a high value, it attains a max, and it attains a min. The funny thing is you see this in this third picture, and you'll see it a couple times up here. Whereas the first scenario in the middle of the page here looks pretty good. You have a closed interval, function's continuous, attains a min and a max. Here's a couple cases that where EVT does not apply. Extreme value theorem doesn't apply to an open interval. In this particular case, you do have a minimum value on this open interval that doesn't contain the endpoints. And I want to say the max is up around here, but there's no way to do that. The function never attains this high value because we said we're not including 2 in the interval. So although you're increasing and your limit, right, as we get closer and closer and closer from the left of that point is going to be up at 5, it never really reaches it if we keep that dot open. So no maximum on this open interval. And look at the third one. We have a closed interval. We actually have a maximum at one of the endpoints, but where a minimum would have been, sure, your function's redefined to have a dot up here, but there's a break in continuity. So in this one, we couldn't really apply the extreme value theorem and say there's going to be a minimum on the interval because we have an open dot. All right, moving along. Let's talk a little bit more about relative extrema because that'll start coming up more and more often in the unit. It says if there is an open interval containing C on which f of C is a maximum, so it's a high point like this hill here on this little open interval, we're going to call that a relative or local max. Relative, we'll say max of the function. No, I'm going to draw an arrow here. I'm not claiming that this is the highest, this is the absolute max, the highest that the graph ever gets to. But in this little closed interval here, it's definitely a peak of the graph. Hang on one second. Sorry for that little pause. Had to turn the lights back on and had to grab a refreshing Dr. Pepper. Okay, back to business. What else is there on here? You also could have a relative min, like this valley that we see on the graph here, as long as in a closed interval, in this little area, that is going to be a min of the graph. So we'll call this a relative minimum. And you're going to notice too, and something I should have been pointing out all along, is that at a relative min or max, automatically, if we're relating this to derivatives, I'm hoping you're already thinking derivative values will be 0 at every local min or max. At every peak or valley that you see on the graph, you're going to have a horizontal tangent line, a slope of 0, meaning the derivative value. If this is a valley at 2, -4, f prime of 2, the derivative at 2, is going to equal 0. Same thing up at that local max up here at x equals 0, f prime of 0. You have a horizontal tangent line and the derivative is 0 there. So that should help us. If we have to look at a function, a fourth degree function like this, I can already picture it, right? A degree 4 polynomial has the potential to have 3 turning points, and you can think of n behavior. And we want to know all of its relative extrema. We want to know at least the x values, right, where you're going to have peaks and valleys of this graph. Use derivatives to do this, right? Calculus has a good way of finding mins and maxes. We can set f prime of x equal to 0. So let's find it first. We want to find where this graph has horizontal tangent lines. We'll use the power rule to get the derivative. So we could say f prime of x equals 12 x to the third minus 48 x squared, and then plus 36x. These would be good times when I start up problems like this, especially if it ever feels like things are going too quickly. It's a good time to pause the video, try the work on your own. See if for this next step you could set this equal to 0 and take your time doing some factoring to get a few values, especially if we're zipping through a little bit too quick. So I'll come back in, right? If you want to pause, feel free. I want to take out a GCF once we've taken a derivative, so maybe a 12x. And we'll have a quadratic left. So an x squared minus 4x plus 3. Okay. So this, we're looking for 3 turning points. I think we might get 3 distinct turning points. You've got a 12x as a factor. You have x minus 3 as a factor. Whoops. And then x also minus 1. And we can set all 3 parts of this equal to 0. You're going to have extreme values at these 3 x values. You're going to have one at 0, derivative would be 0 there, one at 3, and then another one at x equals 1, like that. So if they ask you the location of the relative extrema, you can give those x values. If they really want to know what the max and the min are, those have more to do with the y's. So what you could also do is you can get full out points for these to give the relative extrema. You could go back to the original function, find f of 0, find f of 3, and find f of 1. I won't show the entire plugin now, but you can pause and give it a try. You end up getting 0 if you plug in that, a 5 if you plug in 1. I think I mixed that up. So negative 27 if you plug in 3, and then a 5 if you plug in 1. So these values are where the mins and maxes happen, right? So we could say, we could have 3 ordered pairs. 0, 0 is where a relative extreme value occurs. 3, negative 27 is going to be one of them. And then also 1, 5. I should put parentheses around that. 1, 5. So that's a good thing to keep in mind for starters, is we're definitely concerned in this section with times where the derivative would equal 0. That should be a very common theme for maxes and mins. I'm going to flip the page, and we've got to put a few more vocab words to this. So because finding where the derivative 0 is so critical, it's so important with finding mins and maxes, they nickname these x values where the derivative is 0 critical numbers. Sometimes they're just called critical points or critical values. Also, I'll call them critical points. Is sometimes how you see them in my directions. But it's more than just where the derivative would be 0. I guess I should put this here. So if the derivative is 0, like in this picture, a point of horizontal tangency, or if the derivative is undefined. We've talked before about spots where you've got functions that have a point where you're non-differentiable. At a cusp on a graph, we'll see a couple graphs like this today too. A sharp corner point, an abrupt change in direction where the left and the right side derivatives don't match up, you're going to say the derivative does not exist, and that's definitely a max of this function. So there's 2 cases we look for critical values. Look for where the derivative is 0, or look for where the graph is not differentiable, meaning look for spots where f prime of c is undefined. I'll put equals u n d. Those are great candidates, right, for extreme values of the function when you're looking for local mins and maxes. And these are called critical numbers of the function f. We'll see some other cases later of times that the derivative does not exist. I want to show that on a graph. So it says, can we approximate the critical numbers of the function just by looking at the graph on the open interval shown? Determine whether the function has, can we call these critical numbers the spots where relative maxes happen, relative mins, absolute maxes of the whole function, or absolute mins of the whole function on that open interval. So I'm looking at number 2. I'm looking for times where the derivative might be 0 or undefined, and I'm seeing this turning point. I feel like up here at, let's give the x value, at x equals 2, we have a critical value of this function. So I'm going to say at x equals 2, we'll call that a critical number. If we want to know, if we want to call it something, we can definitely call it an absolute max of the graph, ABS for absolute max. Technically, it's also a relative maximum. It's both. It's the highest the graph ever gets to, and it's also a relative max on this interval. But that's the only one I can find so far. Do you see a spot in number 3 where the derivative value would be 0 again? I feel like this graph, they call it strictly monotonic. It's strictly increasing from left to right, but it has this inflection point in the middle where the graph changes the way that it curves. And I feel like these tangent lines would have positive slopes. They would level off to 0, and they'd go under the function and get more and more steep, get more and more positive. So I've kind of muddled up the drawing a bit. I want to circle the inflection point right in the middle, and we'll call this our critical value. This is a spot where the derivative is 0 at x equals 0. I'm not allowed to call it a relative or local min or max. And I'm just going to say it's neither, right? It's not really any of these. So I'll say, actually, I'll put in parentheses what it's really called. It's called an inflection point of the graph. So we're going to save this conversation until later in the unit when we start talking more about the way functions curve. They curve from something called concave down to concave up. But for now, when we're talking about maxes and mins, we'll leave this one out of the conversation. It's neither a high point nor a low point. 4 has some turns. It looks like I'm looking at like the McDonald's arches here. I would say your derivative is definitely 0 at these 2 values. So you've got horizontal tangent lines here and here. So critical value at x equals 1, critical value at x equals 3. Those are both maximum values. They're absolute and also relative max values. Versus this absolute and relative minimum. So at x equals 2, this is a spot where you can see this is a sharp change in direction. It's not gradual. It'd be really hard to draw one set tangent line here. You actually can't. It's impossible. Derivative is undefined, but you still can call this an absolute or relative minimum of the graph. So that would be a min. So it's kind of nice when you have a visual, you have the graph presented in front of you to be able to decide about where the critical numbers fall. I want to get into a couple more interesting looking functions before we go so we can see if we can find critical points on our own. So it says if f has a relative min or max, then c must be a critical number. So if you wanted to find, if we go into number 5 and we want to know what the mins and maxes are, a good list of candidates would be the critical values. I'm going to leave this one. We'll start it with the next video. So come on back in and join me. I will talk to you soon.